Having introduced the nanoscale and microscale models, now we introduce some theoretical knowledge on how these models work. In the microscopic world, the continuum theory's breakdown is that the chaotic movements of particles urges a probabilistic theory to describe the behavior of a mechanical system. Statistical mechanics is such a theory. It applies to both quantum and classical systems. It is a powerful tool to link the particle-based simulations to the macroscopic properties. To model thermal energy storage material on the micro and nano scale, we need only some basic concepts as preparatory knowledge to the particle-based simulation methods. In a particle system, all possible states can be described by a set of variables consisting of positions and momenta of all particles in the system. The set of variables combined is the phase space. Its distribution function, rho of phase space, is the phase space density. It is determined by the interaction rules of the system. The Hamiltonian gives the total energy of the system. For example, in molecular dynamics, the Hamiltonian is the sum of potential energy and kinetic energy. The explicit expression of potential energy U contains the interaction terms. The dynamics is given by Newton's equations of motion. To find the phase space density and carry out the statistics, we need to firstly define under which condition the systems are in equilibrium. Here comes the definition of ensemble. A thermodynamic ensemble is a set of microstates as points in the phase space that satisfies certain macroscopic thermodynamic properties. The first example here is the NVE ensemble, also named microcanonical ensemble. In an NVE ensemble, it has a constant number of particles, constant volume, and a constant total energy, or Hamiltonian. In physics, the system has a constant n, constant v, and constant e, represents an adiabatic system, without any energy exchange with the rest of the universe. In this case, the phase space density is proportional to the Dirac delta function of h minus E, where h is the Hamiltonian and E is the macroscopic thermodynamic quantity that defines the ensemble. In the second example here, the NVT ensemble, also named canonical ensemble. This is the mostly used ensemble. NVT ensemble describes a system in thermal equilibrium with an external heat bath at temperature T. It also has a constant number of particles n and a constant volume V. To be noted here, the system's microstates can still have instantaneous temperatures. If this is higher than the heat bath temperature, the energy will flow out to the external heat bath, and vice versa. If we measure the macroscopic temperature of the system, it will be T statistically. The third example here is the NPT ensemble, also named isothermal isobaric ensemble. It describes a system with a fixed number of particles n, and it is in thermal equilibrium with an external heat bath at temperature T and in a pressure equilibrium via a frictionless piston with an external pressure P. To calculate the thermodynamic quantities of the ensemble microstates, we use the so-called ensemble average. A thermodynamic quantity O is calculated as an average weighted by the phase space density. So here, for example, the estimator used to calculate temperature of a microstate is twice the kinetic energy of 3K. If we put this into the ensemble average equation using the weighted phase space density, then we can find the average temperature of a system. The partition function describes the total number of microstates of the system. To calculate the phase space density, the partition function is indispensable. And here, at least here, the partition function in NVT ensemble of only one particle. It equals the sum of exponential of negative Hamiltonian over kT. The partition function gives rise to a whole set of thermodynamic quantities of the system, including entropy and free energy. For example, the Helmholtz free energy in NVT system is given by the negative kT times logarithmic of partition function. In this table, the thermodynamic relations, partition functions, and phase space densities are given for three previously introduced ensembles. To be noted, usually the partition function cannot be analytically solved. Therefore, we need to look for indirect ways to approximate the dynamics. Now let's have a look at a very simple example to explain how statistical mechanics works and how to use it to derive macroscopic properties of a toy system made of only one harmonic oscillator. This toy model is in fact very important in understanding crystals. In a crystal, the vibrations can be viewed as a collection of independent harmonic oscillators, and the crystal's properties can be predicted using its phonon mode analysis. In a system with only one harmonic oscillator, its Hamiltonian is simply the sum of kinetic energy and potential energy of the harmonic spring. In an NVT ensemble, recall its definition. NVT ensemble, it means the harmonic oscillator is in a thermal equilibrium with an external heat bath at temperature T. So this means the oscillator can oscillate at any energy level, and it can jump between different energy levels as far as its statistical average is at temperature T. The phase space density in this case is proportional to the exponential of negative Hamiltonian over kT. Solving the Schrödinger equation gives the energy levels of the harmonic oscillator. Hi equals I plus 1 over 2 times h bar omega. Here I equals to 0, 1, 2, 3, 4, and so on. Note, in an NVT ensemble, the probability of finding the oscillator at energy level I is proportional to the exponential of negative energy over kT. So this means the chance of finding an oscillator at higher energy level is actually lower. The partition function here is simply the sum of all possible states of the system weighted by the probability. For the one-particle system, the partition function z can be solved analytically. Now we can use the analytically solved partition function to derive the thermodynamic quantities of the harmonic oscillator. First of all, the free energy, it equals h bar omega over 2 plus another term. The energy E, similarly, is also h bar omega over 2 plus another term. This h bar omega over 2 is actually the 0-point energy of the harmonic oscillator. Note here, the free energy, entropy, and other thermodynamic quantities that are not listed here are all functions of temperature T, a thermodynamic variable that defines the NVT ensemble. To be noted, although the instantaneous temperature can be of any value, its ensemble average is exactly at T. You can prove this as an exercise using the aforementioned equations and the estimator of T.